Hello, and welcome to today's webinar, Safer Chromatography Without Chlorinated Solvents, Avoiding DCM. Today we are joined by Dylan Cavey and Jack Silver, who are both application chemists for Teledyne LABS. Prior to us beginning this presentation, I would like to remind you of a few items. If you happen to experience any audio or video issues during the webinar, please leave and rejoin. This oftentimes will clear those problems. If you have questions, please utilize the questions button, and Dylan and Jack will be happy to answer at the end. The webinar is being recorded, so therefore you will receive an email after to provide you a copy of the webinar. So with that, I would like to welcome Dylan.
Welcome everyone to today's webinar. As previously mentioned, I'm Dylan Cavey, one of Teledyne LABS application chemists, and today we're talking all things dichloromethane, methylene chloride, or DCM for short. As many of you are aware, there are some new restrictions going on about DCM. So we're going to start talking about why that is and dive into some potential alternatives for DCM. Then we're going to talk about a hot problem that we've seen with some of these DCM alternatives when it comes to flash chromatography. And then we'll talk about how to properly equilibrate your guys' flash column so you don't run into some of these issues that we've been seeing here at Teledyne LABS. Then I'll pass it off to my colleague Jack Silver, who will be talking about some alternative methods that avoid using DCM, some reverse phase, some Hillock, and of course we'll touch SFC, supercritical fluid chromatography as well, and the benefits and some workflows that come with SFC. Then we'll end with some examples that previously needed chlorinated solvents, but with SFC they don't. So with all that said, let's get this thing going. All right, working with alternatives to chlorinated solvents. Let's start by talking about why we should be avoiding DCM. Well, first off, DCM has a high bioavailability, and all this means is once DCM enters the body, a high percentage will be able to affect the body. So if we think of a drug with a low bioavailability, it won't be efficient in entering the bloodstream and performing its intended purpose. DCM is quite the opposite. Once it enters the body, it's going to be able to react and cause some harm. And DCM will do this in two different pathways as shown here through these two different enzymes, one in that red and one in that blue. So it's going to be that CYP2E1 and that GSTT1, which is a transferase. Now these two pathways can lead to the formation of formaldehyde and carbon monoxide. And these are reactive species and can cause DNA adduct formation, which leads to mutations in our DNA, which can ultimately lead to cancer. So that's why DCM is labeled as a carcinogen, and it's something that we can't take lightly. When we are in the lab, we need to be safe when handling DCM. And this is also why the EPA has put forth a 2 parts per million inhalation limit on DCM. So wherever you're at right now, whether you're at the office, at your home office, at your house, wherever you're at, imagine that the room you're in has 1 million air particles and only 2 of those can be DCM. That's the inhalation limit that the EPA has put forth, and that was supposed to take effect on August 1st of 2025. So if you're working with DCM, you right now are supposed to be below that limit for an 8-hour period. And a lot of labs and universities, it's going to be difficult to get under that inhalation limit due to infrastructure restrictions. It's going to be very difficult. So that's why a lot of scientists like yourself are trying to move away from DCM. Here are a couple NIH articles speaking on the dangers of DCM. The first one there looked at DCM exposure to mice, where they saw cancer formation in the lungs and the liver of these animals. They also saw some neurological effects as well. The second one looks at a couple different patients in China with methylene chloride poisoning, one of which actually experienced sudden cardiac arrest and caused the patient to actually fall from a significant height. Good news here, though, as the patient was able to survive thanks to some extensive treatments provided by these healthcare professionals. But again, this just speaks to the seriousness that DCM needs to be treated with care, and if it can be avoided, it's probably in the best interest of all of those involved. If DCM is out, well then what can you guys use? And unfortunately, this is not going to be a one answer fits all, because DCM has a unique selectivity. If we look at that Snyder selectivity triangle on your guys' screen right now, you'll see that DCM is in group 5 all by itself. It has a fairly large dipole movement, where those electrons are going to be pulled in between the two chlorine atoms, which gives DCM some polarity, but nothing like that of water or methanol. And this allows DCM to interact with both polar and nonpolar compounds, making it very versatile, just a very versatile solvent. So in order to try to replicate the selectivity of DCM, chemists have been hard at work trying to form some mixtures of solvents that mimic these characteristics of DCM. Now, some of the most common of these alternatives are going to be ethyl acetate ethanol mixture 3:1, MTBE acetone. We've even seen some IPA acetone mixtures as well. And this chart is a really good chart from green chemistry, showing how these DCM alternatives relate to your standard DCM methanol gradients based on their polarity. So we have polarity increasing as you work your way from left to right. At the top, you'll see that chemists that are using these alternatives are actually using alkanes as their A solvent, and then those DCM alternatives as the B solvent. So you can see that 3:1 ethyl acetate ethanol mixture does actually a really good job encompassing the entire polarity range. And you can also see those using that MTBE as that weak solvent is really good for some more polar compounds as well. But this chart will give you an idea of how changing these alternatives is going to affect your guys' chromatography. Now that you have your alternative in place and no longer have to worry about DCM, you think you'd had found your way through the storm and there's only calm waters ahead. Well, not so fast, my friend. Something we've seen here at Teledyne LABS is these DCM alternatives are causing a hot problem in flash chromatography. As we just saw on the previous slide, when we're working with DCM alternatives, you're going to be working more in a traditional normal phase method with those alkanes as your weak solvent and then increasing the polarity with that DCM alternative. Well, if you're working with traditional normal phase methods, you're going to be working with a traditional silica column. And you may have noticed in the past, if you've done normal phase, that when you're equilibrating that silica column, it's going to get hot. And this is called the heat of absorption. And what is happening when you feel that heat is there's some water content on that silica surface, and the water will become displaced when a polar solvent is absorbed onto the silica. Now, this is an exothermic process, so it's going to create some heat, and that's what you will feel if you touch that silica column. But what we've noticed and now seen, thanks to Teledyne FLIR's thermal camera, is these DCM alternatives are creating concentrated heat bands as that polar solvent works its way down the column, which is ultimately resulting in damage to the columns. But even worse, it's potentially damaging the chromatography instruments as well. So let's first look at this thermal video. Now this is just going to be a standard 5% methanol in DCM separation. So we're going to start this video, and you guys can see that heat band start to make its way down the column as we first introduce this solvent. But something I would like to point out is if you look at that temperature in that top left hand corner, we never get above 40 degrees Celsius for this entire separation. Now let's change our solvents here and do one of these DCM alternatives. So now this separation is going to be a 70% heptane in a 30% 9-to-1 IPA in acetone mixture. So one of those solvents we talked about prior as a DCM alternative. Now when we watch this, watch the heat band and watch what happens to the temperature as this heat band works its way down the column. You can see we're just below 40 degrees Celsius here, and eventually this heat band is going to increase significantly. So you can see there we jumped up to 50 degrees, and now this heat band is going to settle on the bottom frit of this column, and we're going to get well above 60 degrees Celsius, even north of 65 degrees Celsius in this run. And I should note, with this FLIR camera, we're looking at the temperature on the outside of the column, so we believe the temperatures on the inside of the column are actually much higher. So this run actually resulted in an overpressure error, which caused us to look further into these heating issues. And what we found was if temperatures reached above 40 degrees Celsius, well, these temperatures were hot enough to start to damage the bottom frit of these columns, as we see here in this photo. The temperatures allowed the frit to become more malleable and would actually cause the frit to be pushed into the bottom exit port of the column. So if you look at that image there, you can see in the middle that part of the frit became so hot and so malleable that the pressure was able to push it into that bottom exit port of the column, and this creates some restriction of that solvent flow and ultimately leads to that overpressure error we saw on the previous slide. So interestingly enough though, if I took the same column and that same mobile phase that we just ran on that previous separation, that 70% cyclohexane and 30% of that 9-to-1 IPA and acetone mixture, and we run it under the same conditions but on our Combi flash torrent system, which is our large scale flash system which has larger ID tubing, which then allows us to run at a lower back pressure. Well, the overpressure error doesn't occur, but the temperatures are still really hot and remain consistent between the next gen and the torrent. So if we look at this graph here, the next gen is going to be the purple trace and the green trace is going to be the torrent. So what you'll notice is about after that one column volume mark, you'll see that the pressure for the next gen gets up to about 75 psi and the torrent remains steady at that 50% psi. And then at that 1.4 column volume mark, you can see the pressure trace for the next gen skyrockets, but the torrent remains consistent around that 50 psi mark. So what we're seeing is, since the temperatures were the same, both were above 40 degrees Celsius, but there's a slight pressure difference, about a 25 psi pressure difference between the next gen and the torrent. Well, what we saw was the temperatures also need to be hot, but we also need a certain amount of pressure to be able to actually push that bottom frit into the bottom exit port of the column. So there's two factors at play here. You need the temperature, but you also need a certain amount of pressure to actually be able to push that bottom frit into the bottom exit port. So here we're going to look at another example with the solvent blend we've been using prior, that 70% cyclohexane, 30% 9-to-1 IPA and acetone mixture. But this time with the FLIR camera, we're also going to add a pressure trace and a 214 nanometer absorbance graph that is synced up to that FLIR infrared thermal camera video. So we're going to start this here, and you guys are going to watch as that solvent blend starts to work its way down the column. Our pressure trace is going to be in blue, and our 214 nanometer absorbance is going to be in that orange color as we make our way through this graph. I'm going to pause it a couple times just to point out a couple key things that will become important to us as we work our way through the webinar that I would like you guys to remember, and we'll make some other points more clear as we work down our way through this. So you can see here we're already above 40 degrees Celsius, and we're going to get a huge UV spike here. So I'm going to pause the video here. You guys can see that we get that huge 214 nanometer spike, and that's from the acetone. So the acetone is starting to elute from the bottom of the column. But if you guys were watching prior to that 214 nanometer spike, our solvent front had already reached the bottom of the column. So we were already eluting some sort of solvent from the bottom of the column, but that polar solvent has to interact with the stationary phase, so it's a little bit behind the solvent front. That's going to become very important to us later down in the webinar, so remember that. You guys can also see, if we look at our pressure, I know it's a little bit hard to see on this graph since it's so small, but it's splitting the difference between 100 psi and 50 psi, so that's around, let's just say, 75 psi. As we've highlighted before, we're at 43.3 degrees Celsius here, so that's hot enough to do any sort of damage to that bottom frit. So let's continue to play this video, see how it turns out. Eventually, you guys are going to see here soon, there's the pressure spike. So this column does overpressure. You guys also saw our internal fractionation arm right there move from the right to the left, which indicates that the pumps have stopped due to that overpressure air. And you guys can see here, we're above 60 degrees Celsius, working our way above 65 degrees Celsius on this separation here. So now let's take the cyclohexane out of our solvent system. So let's just run it in acetone and IPA. Similar to what we saw on the last slide, we're going to have our pressure trace and our UV trace in that lower left-hand corner. And let's just see what we get with this separation. So we're going to start this separation here, and you guys are going to watch as that heat band starts to form. Our pressure trace is going, our 214 nanometer absorbance is going. I will pause this just like I did with the prior slide to point out some interesting and key details that you guys will see. So here you guys can start to see we get that initial 214 nanometer elution. We start to see that absorbance there, our pressure spike still going on, still steady throughout this. So we're starting to elute some of that acetone, and now we've reached a steady state here at roughly around just above 80 psi. So again, I know it's hard to see how small that graph is, but that pressure trace is just hovering just above 80 psi. So if you guys remember back to the prior slide, that separation got to roughly around 75 psi, we said, and it had temperatures north of 40 degrees Celsius. Well, that one resulted in an overpressure. But if you look at your screen right now, look at the temperature. It's at 41.1 degrees Celsius. That's hot enough to do damage to the bottom frit, and we actually have a pressure that is higher than what we just saw on the previous separation. So as you guys would imagine, I would believe, we all would believe, that this would also result in an overpressure error, but watch what happens. We actually never see a pressure spike on this separation. So that means that there has to be something else that's playing a role in these overpressure errors and causing damage to these columns, because this one did have the adequate amount of heat and it had the adequate amount of pressure to push that bottom frit into the bottom exit port. But as you guys can see here, it's eluting all of that heat off of the column. The column's actually starting to become completely equilibrated, and you guys can see that pressure and that UV absorbance is starting to flatline. This column actually becomes completely equilibrated and would actually be able to do a chromatography separation. So this means there's yet another factor that is playing a role in these overpressure errors and column damages. As we stated earlier on in this webinar, the heat generated on these silica columns is due to water being displaced on that silica surface, which got us wondering if the water that's being displaced, could that be playing a role in all of this? Water is not going to be soluble in any of those alkanes that a lot of these DCM alternatives would use, but it would be soluble in what we just saw in that IPA and acetone mixture. So what I did is I took a bunch of 40-gram silica columns and I filled them either with water or I filled them with alkanes, and then I tried to pump the opposite through them. So for instance, if I filled a column with water, then I would try to pump 100% hexanes through it, or fill the column with hexanes and then try to pump 100% water through it. I then monitored the pressures for these columns, and you guys can see those pressure traces below in that graph there. So the columns that produced the most pressure were the columns filled with alkanes, and then water was tried to be pumped through them. And the more we thought about this, the more it actually made sense. So if you remember from the previous two slides, we could see a 214 nanometer spike that I pointed out to you guys from that solvent, from that acetone hitting the bottom of the column, then making its way to the flow cell. Well, the polar solvent, as I mentioned, is going to interact with that stationary phase. So it's going to be held up a little bit. So what's going to hit the bottom of the column first would be the alkanes, right? Because it's going to zoom past the stationary phase and it's going to reach the bottom of the column first. But we have to remember that since water is being displaced by that polar solvent, the water is going to hit the bottom of the column just before that polar solvent does, so just before that 214 nanometer spike. But guess what's already at the bottom of the column? Well, you're going to have that alkane. So what we're seeing in this experiment is that it's going to increase that pressure because that alkane is going to be filled, let's say that's filled the column, and then you're trying to push water through it. So there's also some miscibility issues between the water and the alkanes. So this is yet another factor that plays a role in this hot problem. Now you all are probably wondering, if I can't use DCM for flash and the alternatives are going to damage my column and potentially even damage my system, what can I do? I have samples I have to separate. Well, we can use these alternatives. We just have to be smart about how we are equilibrating our columns. So we recommend equilibrating your column at a low %B or a low percentage of that DCM alternative to limit the amount of water being displaced at once. So you guys can see in this video here, we're equilibrating this column at a low %B, so a low % of that 9:1 in IPA and acetone mixture, and still running cyclohexane as our strong solvent in this case. And you guys can see we're just below or just above room temperature throughout this whole separation. And right here you can see that column's going completely blue, which means that that heat is off the column. It's ready to go for a chromatography separation. So we're nowhere close to that 40 degrees Celsius mark, which is a really good sign. So we recommend equilibrating at this low %B for a couple column volumes, 3 to 4 column volumes, to ensure that the heat and the water are pushed off the column as this video shows. And then you guys can increase your %B to your starting percentage. If you guys are doing a gradient or if you're doing an isocratic run at a higher %B, that's when you guys can increase that %B and do a brief equilibration there with your guys' starting solvent composition. And this will allow you guys to use these DCM alternatives in a safe manner and get your guys' samples separated. So with that, I'd like to hand this webinar off to my colleague Jack Silver, and he'll walk you guys through some other ways around using DCM, whether it's using reverse phase, Hillock, and maybe even some SFC to give you guys some options as well to try to move away from DCM. Jack, it's all yours.
At this point in the presentation, we're going to talk about chromatography alternatives to chlorinated solvents. And this way we could avoid some of the problems that Dylan mentioned. One replacement for chlorinated solvents is reverse phase, because those compounds that use DCM are usually polar. As an example, piperine was purified with a chloroform methanol gradient on silica. However, using a crude extract and a water methanol gradient, I could run it on C18 with good peak shape. A solvent modifier such as TFA or formic or acetic acid could have improved the peak shape here, but it's good enough for flash chromatography. A scouting gradient was run on a ReadySep 4.6 millimeter column on an analytical HPLC, and a preparative gradient was calculated. 125 milligrams was loaded on a 50-gram ReadySep Gold C18 column, and we got a very nice separation. Hillic, or aqueous normal phase, is also an alternative to chlorinated solvents. You use columns such as alumina, silica, or amine. Weak solvents can be acetone or acetonitrile or other water-miscible solvents, while the strong solvent is water, which might contain solvent modifiers if you need them. The examples at right used methanol water to replace a DCM methanol gradient, which is shown at top. Adenine and caffeine were resolved on silica. However, also using silica, the same two compounds were adsorbed on silica and run on a 24-gram column using acetonitrile water. One thing to note is that we do not start at 0% B solvent. We equilibrate at a few percent water so that the stationary phase gets a nice water coating that allows Hillic to run properly. Amine columns are also a good choice for Hillic. The top run is a silica column run with DCM methanol, and I'm resolving caffeine and theophylline. Using a similar size amine column with no additives, I use acetonitrile water, and I got much better resolution. Amine column is good for basic compounds because you don't need a solvent modifier, and especially do not use acidic modifiers on amine columns. Supercritical fluid chromatography can be a replacement for chlorinated solvents. These the solvents are carbon dioxide and methanol or another alcohol, and so it's very inexpensive. The dry down is very rapid because the carbon dioxide is removed prior to fractionation, and the remaining solvents, again, usually an alcohol, are volatile. The solvents are less toxic than most normal phase solvents. We're not using hexane or cyclohexane or heptane or anything like that. Older SFC systems needed a lot of user interventions, but we'll show you that the AccuPrep SFC is very stable and just runs and is very reproducible. We have a very easy method development on our SFC, and the examples shown here are all achiral compounds. The top run on the right was run about 2 years ago, or actually run late last year. And the bottom right was run 2 years before that. Different silica columns and different AccuPrep SFC instruments were used, yet one can see that the separation is very nearly identical. And below, yes, it looks like a mess, but it's a stacked injection that was run over 7.5 hours with no user intervention. The system just simply kept injecting and kept running, and the user came back later and just collected their samples from the bottles and dried them down. Liquid chromatography has many replacements for chlorinated solvents, and the method development for these is generally involves thin layer chromatography plate. There are many replacement solvents for dichloromethane, and they are listed here as weak solvents, and the strong solvents are generally methanol or a mixture of 3-to-1 ethyl acetate methanol, which is a commercially available compound, a commercially available solvent. You note that the TLC plate on the left shows that the DCM makes nice spots that are nice and circular, and if you ran that in a column, there would be nice symmetrical peaks, whereas the substitutes for dichloromethane don't show circular spots. They show fronting or tailing or streaking, and that would show up on a column as a poor peak shape. People have tried to use thin layer chromatography plates for SFC method development with results from mere correlation to no correlation at all. And furthermore, they find the need to use chlorinated solvents for TLC method development for SFC. The focus gradient generator that's built into all of Teledyne's chromatography system is a better option for SFC method development because you don't need chlorinated solvents at all, and it gives very good results as to how a very good indication about how the column will run. So to set up the time on target algorithm, a model compound is run isocratically and the solvent composition is adjusted to cause the desired retention time on a column. This solvent composition is noted for the next step where we run a scouting gradient on either an analytical or the prep system. We use a matching column and we use the same solvent as we use for the isocratic run. And wherever the model comes out during that scouting gradient is deemed to be the same solvent composition used in the isocratic method. The difference between the time that the gradient reached that programmed solvent composition and the time the compound elutes is called the apparent gradient delay. And we then use the same scouting gradient on other compounds that we've synthesized, and we apply that apparent gradient delay to then calculate the solvent composition for focused or isocratic method. An example of a DCM replacement test compound is as acetaminophen, and it's used in liquid chromatography. The focus gradient generator was used to run acetaminophen and calculate a isocratic method on a silica column with methanol with good peak shape and the desired retention time. Piperine was used earlier with the reverse phase example. The extract was screened on an analytical SFC with a silica column. Methanol on top showed elution, but the piperine was close to other compounds, and using 2-propanol showed better resolution between the piperine and the impurities. A focus gradient was calculated and then purified on the bottom trace, bottom run with a silica column, SFC. And this is a short example of a solvent screen where I tried different solvents to try to find the best purification method. Another example is SM102, which is an artificial lipid used to encapsulate messenger RNA for vaccines. As you can see from the structure below, it has very few chromophores, so detection with ELSD and mass spec was used. This compound was run on flash chromatography with DCM methanol. We used an amine column, and we see in the focus gradient at the bottom that there is an impurity that shows up on the ELSD that co-elutes with the SM102. We also tried reverse phase, but the peak shape was very poor even with additives. So now let's see if it runs on SFC. Silica with ethanol top shows very poor peak shape. It also has late elution, and with late elution, I'll try a stronger solvent. That is a solvent that's more polar for earlier elution, and I would do an additive. I add that to improve the peak shape. So this is all run with a silica column. So I tried it again with methanol with 0.1% ammonia, not ammonium hydroxide, and we see greatly improved peak shape and earlier retention, and we will see that most, perhaps all compounds can be run on silica. Also, SM102 was subjected to a column screen, and so now I try a diamine column. Diamine is similar to the amine column that we used earlier for the flash chromatography, and we used ethanol as a co-solvent in this case because the diamine is somewhat less polar than the silica, and so a weaker solvent seems to work well. We got good peak shape, and you can see in the bottom trace that it's very well resolved from the impurity, and the focus gradient ran very well. There was no additive needed at all. This section will discuss natural products, and these are all small molecules with applicability to medicinal chemistry or general organic synthesis. The compounds were subjected to both a column screen where I tried different columns, and also using a solvent modifier screen with silica. So I ran the compounds on silica, and I ran methanol with no additives. Also, I ran compounds with acid or basic modifiers. All of the compounds listed after this use chlorinated solvent for their purification, but were not needed for SFC at all. The first one I will discuss is curcumin. This was pre-purified extract. I pre-purified it on a flash C18 column and got the large peak. I then took the peak and ran it on a column screen. The co-solvent in all cases was methanol, and at first glance I have good peak shape in all of them. However, the PEI column resolved the different compounds that were in the curcumin with no additives. I will note that these compounds were also resolved with SFC with a BEH column with an oxalic acid additive. However, the PEI needed no additive. So I took my scouting run and I focused on the first eluting peak of the three compounds. And the isocratic method ran very well. And then I made that into a stacked injection. So in about 2 injections, I was ready to do a stacked injection. Now note this isn't a chiral compound, but I was able to do a stacked injection and purify all of my crude extract, or my somewhat crude extract, very quickly. Here's a summary of some other compounds. Instead of giving you all of the different chromatograms, I'll list the columns that are tested in this table. And if the column gave a good peak for a scouting run, the focus gradient range is listed. Otherwise, I'll just describe the chromatogram. Macrine is an alkaloid, and as expected, it ran well with 4-ethylpyridine, PEI, and silica with a basic additive. Without an additive, it also ran as well too, since it gave a broad peak without an additive. Another alkaloid is related to the compound earlier. It's oxymacrine. This compound is very polar because the nitrogen has a formal positive charge and the oxygen is formally negative charge. It ran with 4-ethylpyridine. It had some tailing with PEI. However, on silica, it ran very well with a 58 to 68% B gradient. 4-ethylpyridine also worked pretty well. It needed less methanol and no additive. The silica 0.5% isopropylamine was the additive, but note that the elution needed more than 50% co-solvent. Many or most SFCs can't run stably above 50% co-solvent. So it's kind of nice to have the ability to run at a higher co-solvent concentration if needed. Cytosine is another alkaloid, and good elution was seen with poor ethylpyridine and PEI. And once again, silica worked with isopropylamine. Now let's go over to phenolic compounds, which are acidic. I did not run columns with basic character, but this ran very nicely with silica. Here's another phenolic compound. This compound ran well with diol as opposed to the previous slide. It needed a formic acid modifier to run well on silica. And epicatechin is commonly found with the other two compounds. And I ran it just to show that it can be resolved from the other compounds, as it would occur as an impurity. It ran with ethanol or methanol with formic acid, and adding the acid made the compound less polar. It made sure that the phenolic group stayed protonated, and so it needed a slightly lower concentration of co-solvent to elute compared to running it without the formic acid. Silica is able to purify all of the compounds tested so far, with the possible exception of the curcumin, which came out as multiple peaks on the PEI. The reference below lists many compounds analyzed by SFC with additives, and a partial list of these compounds is shown on the right. Adding 5% water to the methanol would extend the polarity range. You don't want to add more than 5%, otherwise the water doesn't stay very well in solution. But it does seem that silica acts in the same fashion as reverse phase C18 for supercritical fluid chromatography, in that you can run almost anything on it, just as you can run almost anything in reverse phase with C18. So here's a workflow for SFC. The first thing is to verify the sample dissolves in the co-solvent, and I generally start with methanol. There's two reasons for verifying that the sample dissolves in the co-solvent. One of them is if it dissolves well in the co-solvent, you can have better loading and generally better peak shape. The other reason is after the compound elutes from the column, we get rid of the carbon dioxide with a gas liquid separator. And if the compound does not dissolve in the co-solvent, it is possible that it will precipitate out over there. And again, your sample will be spread over multiple tubes instead of being potentially sharp as it ran out. So start with methanol and then go to less polar solvents. So methanol, you could try ethanol, isopropanol, even ethyl acetate will work as well. If it's a known compound and you know that the compound is acidic or basic, just use the solvent modifier as needed. Acidic compounds would work well with acetic acid or formic acid. Basic compounds, I like to use ammonia or isopropylamine. If it's something that's neutral, just use a plain solvent and run the scouting run. If the compound elutes too early, use a weaker solvent, provided it dissolves in that solvent. Calculate the focus gradient and purify, and that's your solvent. That's your silica solvent screening. The diagram at right shows a column screen. So again, you do the same solubility check as I described above in step 1 over there. Run a scouting gradient with the different columns and choose the column with the best peak shape and resolution. And you might find that you need an additives or you might need a weaker solvent. And this is exactly, the column screening is exactly what's typically done with chiral columns. When you just try different columns and see which one works best. So SFC can replace the need for chlorinated solvents in chromatography. The citations below listed 125 different studies of natural products purified with SFC. and both polar and non-polar compounds were evaluated. And of those, only one of them used DCM as an SFC solvent, less than 1% of the compounds tested. The paper cited earlier ran 30 compounds of silica without the need for chlorinated solvents. So silica appears to be a nearly universal column for SFC. Scouting runs and focus gradients allow column and solvent screening with easy method development. And scouting runs also allow optimization for detection for improved sample recovery, but that is another webinar. But very briefly, a scouting run allows you to look at the UV spectrum and perhaps choose a more optimal UV absorbance, or potentially if you're using a mass spectrometer, your molecular ion peak might be weak, but a fragment from that molecule might be a very strong peak and allow faster and easier detection of the compound to increase the recovery.
Well, thank you, Dylan and Jack, for sharing your expertise. And it looks like we've received a few questions. Jack, can you take the first question for us?
I certainly can. The first question is on the C18 run of piperine. The compound eluted slightly later in the gradient than expected. Why did that happen? A solvent modifier such as trifluoroacetic acid would have been more appropriate for this run because this is a ionizable compound, and the TFA would have improved the peak shape and also improved the retention accuracy. The compound was probably ionized slightly or converting slightly during the scouting gradient. Dylan, this question looks like something you can answer.
Yeah, we have a couple questions coming in about the column heat with those flash columns. So the first one we have here is, did any DCM methanol gradients ever result in any overpressure errors? And we didn't see that with any of our test results. As we showed earlier, the DCM methanol gradients that we saw were just below that 40 degrees Celsius mark, which is where we started to see that frit become more malleable. So we didn't see anything go above that 40 degrees Celsius mark. Also, when you're working with those solvents, you're going to see lower pressure. And the other thing you have to think about is that miscibility issue that we saw with a lot of those alkanes. You're not going to have that miscibility issue with these two solvents, so you're not going to form that wall at that bottom of the column, which then results into that pressure spike. So no, we didn't see anything with that DCM methanol gradients. Jack, this next question looks like it's for you.
Look, the question is, why didn't I start the Hillock runs at 0% B? And the reason for that is the column really isn't equilibrated at 0% B. It needs a layer of the more polar solvent to run properly and to partition the compounds between a thin solvent layer on the surface of the silica or alumina and the mobile phase. Dylan, here's another one for you.
Yeah, next question here is, how should I equilibrate if I'm using a gradient method? So again, we're talking about those flash methods. And if you're using a gradient method, if you're starting at a low percent B with any of these DCM substitutions, you're going to equilibrate at that low percent B. And that's exactly what we want, is we want you to introduce that strong solvent at a low percentage to get rid of any of that water and that heat off the column. But if you're starting a gradient, let's say at like 50% that strong solvent, and anything above 20 to 30%, we're going to want to still equilibrate that at a low percent B. So if you can establish a method where you are equilibrating the column at 5% of that strong solvent for a couple column volumes to try to get rid of any of that water, get rid of any of that heat from your guys' column, then actually start your equilibration at that 50%, you guys are going to see a lot better results. Jack, this next one, again, looks like it's for you.
Okay, this one's kind of interesting. Can you use acidic additives or solvent modifiers with columns with basic bonded phases? And one should not need additives for these columns, such as the amine, diamine, and PEI, because these have a surface modification that makes them basic, and you shouldn't need to use any additives for them at all. Dylan, you're up for this one.
Another question coming in here, if I lower the flow rate, do I still have to equilibrate at a lower percent B? And this is a good question. As you would think, if you're lowering that flow rate, you're gonna put less pressure on the system. And that will then most likely, you would think, limit the amount of that frit likelihood to be pushed into that bottom exit port of the column. But actually what we saw when we lowered the flow rate on any of these columns is the heat's actually going to stay on the column longer. So you're going to actually see higher temperatures if you lower the flow rate, which allows the frit to become even hotter. It becomes more malleable. So you don't even need those higher pressures to push that frit into the bottom of the column. So we actually saw more overpressure errors when we dropped the flow rate. It would actually be better if you could increase the flow rate from what we've seen. Because if you increase the flow rate, then you're actually pushing the heat through the column quicker to where it doesn't build up on that bottom frit. But the problem with increasing the flow rate is then you're increasing the pressure. And some of these columns, you're working already up at the upper limits of the flow rates for these instruments, so you actually can't increase the flow rate. You could only decrease the flow rate. So we do not recommend decreasing the flow rate for any of those equilibrations. Jack, back to you.
Okay, this one is an interesting question. Why didn't you run the phenolic compounds with the basic columns? Well, the surface of the column is basic, and when I'm running a base, the basic compounds tend to act less polar. However, acidic compounds tend to work in the opposite fashion. I've got an acid and a base interacting, and so those compounds tend to act more polar and might retain longer and might not even come off. On regular liquid chromatography, acidic compounds tend to stick on basic columns.
Well, thank you, gentlemen, for answering these questions for us today. If your question that you submitted was not responded to, we will answer it via email. As I shared earlier, this webinar is being recorded, and the recording will be made available in the near future. Thank you again, and we hope to see you again next time.